In this video we are going to discuss about how we generate prime numbers as well as how we will be testing the prime number. So, generating prime number, we have two conventional methods. The first method is known as Mersenne method. Now, Mersenne method says that MP is equal to 2 to the power P minus 1. It means it is going to generate a number if P is prime. It means if P is prime, whatever value MP will be getting, that will also be a prime number. So, for example, if you take that, suppose P is equal to 2. So, what will be happening with MP? 2 to the power 2 minus 1, that is equal to 3, and 3 is also a prime number. Suppose we are taking an example that P is equal to 3. So, in that case, MP will be 2 to the power 3 minus 1, that is 7. 7 is also a prime number. Suppose P is equal to 4. So, MP will be 2 to the power 4 minus 1, that is 16 minus 1, that is 15. So, at this particular juncture, it is going to fail. So, it means Mersenne method is not applicable for generating a prime number. It is applicable only for the value up to P is equal to 3, because whenever the P value is going to be 4, it is going to fail. So, Mersenne method is not applicable at all after when the P value of P is more than 4 or 4 itself. So, the second method is the Fermat's method. So, in this Fermat's method says that Fn is equal to 2 to the power n plus 1. It means for any value of n, if we put in this right hand side, whatever value we will be getting for Fn, that will be a prime number. Now, let us check how it happens. Suppose n is equal to 3. So, with n is equal to 3, the value of Fn will become 2 to the power 3 plus 1. So, 2 to the power 3 is equal to 8. So, 2 to the power 8 plus 1. So, 2 to the power 8 plus 1, that is equal to 257. So, of course, this 257 is a prime number. But whenever we go beyond n is equal to 4, or even we are checking for n is equal to 4, this method is also going to fail, because it may be possible that the number which we will be getting, it may be a prime number, it may not be it may be a composite number. So, it means as far as the Mersenne method is concerned, it is not, because in cryptography, in most of the cases, we have to generate a large prime number, and though these two, both the methods are not applicable to that. So, we have to devise, we have to look for another. So, the other methods may be applicable for generating the prime number, but it will be better that we consider a particular number and let us test whether that number is a prime number or not. So, that is called primality testing. That you consider a particular number and then try to find out whether that number is a prime number or not. Because the idea is to create a large prime number, because in most of the cryptography algorithm, we have to look and consider a large prime number, and then the algorithm can work. So, we need an algorithm which can correctly as well as efficiently test a large integer, whether that number is a prime number or that number is a composite number. So, there are two broad categories of primality testing. One is deterministic algorithm. And second one is probabilistic. Deterministic algorithm is a kind of algorithm in which it is sure that the number which will be tested, it will be giving you the correct result in the form that the number is a prime number or the number is a composite number. Means there is a guarantee that you will get a correct answer. But probabilistic algorithm is such kind of algorithm where we have the probability that it may give that the number is a prime number or the number may be a composite number. But if the number will be a prime number, definitely the probabilistic algorithm will be giving the answer in the form of a prime number. But there are certain probability that it is going to give the composite number. So as far as the comparison of deterministic algorithm and the probabilistic algorithm is, deterministic algorithm always gives the correct answer that the number is a prime number or number is a composite number. But this probabilistic algorithm is a kind of algorithm in which most of the cases it declares that the number is a prime number. If the number is a prime number, it will definitely declare. But it is possible with some lower probability that it may declare it as a composite number. So the first algorithm which comes under the category of uh, a deterministic algorithm, let us first discuss the deterministic algorithm. That algorithm is the divisibility algorithm. As I told you that deterministic algorithm accepts an integer and always outputs the result, whether the result is a prime number or is a composite number. So divisibility algorithm, we have already discussed this divisibility algorithm in the previous lecture also. The divisibility algorithm is a very simple one in which we have an integer which will be considered. We take the square root of that value and the square root of that value and all the prime number which are less than that square root value will be tested for that particular number. If it is going to divide, it will be giving you the composite number, and if it is not able to divide, then that number will be a prime number. So we have a certain algorithm. So in this divisibility algorithm, we always test from 2 to square root of n. I have given an example. Suppose n is equal to 97, which we have to test that the number is a prime number or not. So what we will do, we will take the square root of 97. So 97 may be a whole square or it may not be. So what we will look for the number which is less than 97 and is a perfect square. So of course it is 81. 81 is a perfect square. So it means 9. So the range of testing will be from 2 to 9. So whatever integer values, whatever prime values in between, lying in between 2 to 9, that numbers will be going to test the 97 by the division. So 2, 3, 5, 7. These are the 4 numbers which are the prime number in between 2 and 9. So 97 will be divided by 2 first, then 3, then 5, then 7, and if it is not able to divide 97, we declare that 97 is a prime number, otherwise not. So we have an algorithm for that, and let us know what is that algorithm. So this is the algorithm which is known as divisibility algorithm, which comes under the category of deterministic algorithm, in which first of all we consider r is equal to 2. while r is less than square root of n, meaning thereby you have to consider n which has to be tested for its primeness. And so we will start from 2 till now. This process, this iteration will go on until the value of r is less than under n. If r is able to divide n, then we will return and say that it is a composite number. But if it is not so, then what we will do, we will increase r is equal to r plus 1, and then so in this way it goes on, and ultimately if any number is not going to divide 97, then in that case we say that it will return a prime number. But the problem is that this algorithm is good, but efficiency is concerned, it is less efficient, because if you are testing a very large number, then you have to go and do the same process of division for many numbers, and it will take a lot of time. And that is why the bit operational complexity of the divisibility algorithm is exponential. The bit complexity of this divisibility algorithm is exponential. Of course, this method is going to give you the idea that the number will be, it will be giving the result, correct result. If the number is a prime, it will declare that it is a prime. But if it is a composite, it will declare it will be a composite. But due to this problem, we have to go for the another algorithm which lies under the category of probabilistic algorithm. So what is that? Now in probabilistic algorithm, as I told you earlier also, this algorithm does not guarantee the correctness of the result. However, the probability of error it is trying to it is already tried that the probability of error should be minimized, and ultimately whatever it will result, it will give in the form of a correct result, and that result should be correct in most of the time. So if the probability is x zeta, it is going to give the result, the probability of getting the correct result is x zeta, but the probability of getting the wrong result, it is 1 minus x zeta. So what are the different methods which lies under the category of probabilistic algorithm? The first one is Fermat's test. Now as far as the Fermat's test is concerned, it says that if n is prime, then a to the power n minus 1 will be congruent to 1 mod n. This means that if n is prime, then a minus 1 will be congruent to 1 mod n. But it does not mean that if the congruence is going to be true, that is 1 mod n, it is not necessary that n is a prime number. Now you see the difference of statement. If n is prime, and if the value of a to the power n minus 1 mod n is 1, it means the number n is prime number. But for any value by which a to the power n minus 1 is coming to be 1, it does not mean that n is a prime number. So meaning thereby left hand side is going to give you the result of the right hand side. If a to the power n minus 1 mod n is equal to 1, then n will be a prime number. But if any value for which a to the power n minus, if the congruence is going to be satisfied, that is value is 1 mod n, it does not guarantee that n will be a prime number. So if n is prime, then a to the power n minus 1 will be congruent to 1 mod n. But if n is composite, then a to the power n minus 1, then it is possible that a to the power n minus 1 is congruent to 1 mod n. See the difference. If n is prime, it will give the correct result. But it may be possible that if n is composite, then it is possible that a to the power n minus 1 is equal to 1 mod n. For example, if A is equal to 3 and suppose P is equal to 5. A is equal to 3 and P is equal to 5, then 3 to the power 5 minus 1, it will be equal to 3 to the power 4 mod 5. 3 to the power 4 mod 5 will be equal to 3 square into 3 square mod 5, that is 9 into 9 mod 5, 9 mod 5, so it means 16. 4 into 4 mod 5, that is 16 mod 5, that is equal to 1. So it means this number is a prime number. It means 5 is prime. So if the number which is being tested is really a prime number, the result it is going to give the correct. But it may be possible that if we test for 6 and 6 is not a prime number, then it may be possible that for 6 the result will be coming to 1. So that is why we have to consider this particular test for testing the primeness of the number in a very correct manner, so that whatever number we are testing, it should be prime, then only it will give the result as a prime, otherwise it is not going to give the result as a prime. And if the number may be a composite, it may be possible that the result will be coming as 1. So the second method is the square root method. Square root test. This is the second. Square root test, what is that? In modular arithmetic, if n is prime, then square root of 1 is either 1 plus 1 or minus 1. But if n is composite, if n is prime, if n is composite, then square root of 1 is plus 1 or minus 1, but there may be other roots also. The meaning is very simple, that in modular arithmetic, if n is a prime number, then the square root of 1 will be either plus 1 or minus 1. But if n is a composite and then we take the square root of 1, then the possibility is that the square root of 1 will be plus 1 or minus 1, or it may be possible there will be some other roots also. So let us check whether the square, let us check for n is equal to 7 first. So if n is equal to 7, and we know that 7 is equal to prime. So let us check for that. So 1 square will be equal to 1 mod 7. 2 square is equal to 4 mod 7. 3 square is equal to 2 mod 7. Minus 1 square is equal to 1 mod 7. Minus 2 square is equal to 4 mod 7. Minus 3 square is equal to 2 mod 7. Now if you take 4 square, it will be 2 mod 7. Minus 4 square is equal to 2 mod 7. It means if you take the square root of, now whenever you are squaring the value left hand side, so if you take the square root, if we take the square root of this, if we take the square root of this, the value of square root of 1 is coming as a plus 1 or minus 1, and no other roots are available, because here it is 4, here it is 2, here is 2, Here again it is 4, 2, 2, and no number is going to give the result in the left hand side as 1. Meaning thereby here we are getting 4, here we are getting 2, here we are getting 2, here we are getting 4, and so on. So it means 7 is a prime number. Now let us test for another number. Let us test it for n is equal to 8. If n is equal to 8, what happens? Let us check. 1 square is equal to 1 mod 8 minus 1 square is equal to 1 mod 8. Now 3 square is again 1 mod 8 minus 3 square is equal to 1 mod 8. So it means we are getting different value. If we take the square root both the sides, square root of 1 is equal to plus 1, square root of 1 is minus 1. Here we take the square root of 1, so the square root is coming as 3. Here we are taking square root, it is coming as minus 3. It means n is a whatever value 8 is a composite number. Why? Because if this number is a prime number, whenever we take the square root of 1, it should be coming as 1. If we are getting plus, if the square root of 1 is plus 1 and minus 1, and besides that there are some other roots, then in that case we can say that the number is a prime number. Because in this case, if we take the square root both the sides, the square root of 1 is coming as 3. Here we are taking square root, so square root of 1 is 1. So for the primeness of the number, it is necessary that the square root of 1 should be only plus 1 or minus 1. But if it is so that the square root of 1 is plus 1, minus 1, and besides that we have some more values, that number is a composite number. Let us test for n is equal to 17. So 1 square is equal to 1 mod 17, 2 square is equal to 4 mod 17, 3 square is equal to 9 mod 17. Similarly, minus 4 square is equal to 16 mod 17, 5 square is 25, 8 mod 17, 6 square is 36, 2 mod 8 17, 7 square is 49, 49 means again 15 mod 17. So no value besides 1, no value is getting here 1. Every value is different. So when we take square root of 1, it is only plus 1, or in minus case it will be minus 1. So in that case we will say that n is equal to 17 is a prime number. So these are the two different tests which comes under the category of primality testing, that is the square root test as well as the Furness test. Now there is another test which combines both the tests, the multiplication as well as the square root technique, to find out whether the integer which has been considered, whether that integer is a prime number or not, and that test is known as Miller-Rabin test. What is Miller-Rabin? Now, as I told you that it combines Fermat's test as well as the square root test to find out the strong pseudo prime number. What is a strong pseudo prime number? A strong pseudo prime number is a number with the highest probability that the number is a prime number. That number is known as, the number with the highest probability that it is a prime number is known as a strong pseudo prime number. Now in this particular test, instead of obtaining the result in the form of a to the power n minus 1 that we are using in the Fermat's test, we change the value of n minus 1 in some other form. And what is that? A to the power n minus 1 is considered as m into 2 to the power k. So instead of calculating a to the power n minus 1, we calculate a to the power m into 2 to the power k. Here we consider n minus 1 as m, because in the Fermat's test we are calculating the 2 to the power n minus 1. So what we do, instead of computing a to the 2 to the power or a to the power n minus 1, we compute n minus 1 we consider as m into 2 to the power k. M into 2 to the power k means we have to compute a to the power m into 2 to the power k. Instead of calculating a to the power n minus 1, we will compute a to the power m into 2 to the power k. So, a to the power n minus 1 will become a to the power m into 2 to the power k. This means that a to the power m to the power 2 to the power k. It means that you can write it as a to the power m to the power k to the power k to the power k, sorry, to the power 2 to the power 2 to the power 2 up to k times. So, what we do, instead of calculating a to the power n minus 1, we calculate a to the power m to the power 2 up to k times. And the benefit is that the square root is performed, and if a square root fails, we stop. And how is the what is the algorithm behind that? Let us go for the algorithm. Miller-Rabin test algorithm is like this: find m and k such that n minus 1 is equal to m into 2 to the power k. Consider t as a to the power m mod n. If t is equal to plus minus 1, then we return and say that a prime. For I is equal to 1 to k minus 1, where k minus 1 is maximum number of steps. What we do? We square t is equal to t square mod n. If t is equal to plus 1, return a composite. If t is equal to minus 1, return a prime. Then we close that, return a composite. So let us understand this algorithm, which is Miller-Rabin test, which is tested on n and a. N is the number which has to be tested for its primeness, and a is considered as a base. So with that, what do you have to do? We have to consider n minus 1, and we have to change n minus 1 into m into 2 to the power k. And then we will first calculate t is equal to a to the power m mod n. If a to the power m mod n, if the value of t is, find out that it is plus 1 or minus 1, we will return that number is a prime number. We will now go forward. But if we are not able to get t is equal to plus minus 1, then what do you have to do? We have to do the iteration process, and we have to use the square methods. So I will start from 1 to k minus 1, where k minus 1 is the maximum number step. Suppose the value of k is 4, so it will iterate 3 times. 1, 2, first the value of I will be 1, then it will be 2, then it will be 3. And then for value of I is equal to 1, we will do the square process. The t is equal to t square mod n. If t is equal to plus 1, we return that, we say that it is a composite number. But if t is minus 1, we say that it is a prime number. And if all the tests are gone, This test is over, this test is over. This is the iteration process from 1 to k minus 1, and ultimately nothing, no result is coming. We will declare that the number is a composite number. So let us go with an example, and then now let us test 561, whether this 561 is able to pass the test of the primeness or not. So if 561 is considered, and suppose we consider that base A is equal to 2, then n is 561. So n minus 1 will be 561 minus 1, that is 560. So this value 561, 560 can be considered as 35 into 2 to the power 4. So it means m is equal to 35, a is equal to 2, and k is equal to 4. So what we have done, we have to test 561, considering the base is equal to 2, n minus 1 becomes 560. This 560 is factored as 35 into 2 to the power 4, where m will be equal to 35, a will be 2, and k will be equal to 4. So first of all, we do the initialization process and try to compute the value of t. The value of t will be equal to 2 to the power a to the power m. So a is 2, to m is 35. So 2 to the power 35 mod 561, and that value comes around 263 mod 561. I have already calculated it, just not to waste the time. If you consider a to the power 32 to the power 35 and you take the mod value of 561, you will be getting 263. Now this 263, here it says that if t is equal to plus minus 1, return that it is a prime, but it is coming around 263. So we cannot say that the 561 is a prime number or not. So we have to go for the further steps. Now here the step says that I will start from 1 to k minus 1. Here the value of k is equal to 4. So it means the iteration process, the first value of I will be 1, second value will be 2, third value will be 3. So considering that k is equal to 1 first. So suppose k is equal to 1. So what we have to do, we have to calculate the value of next value of t, and that value of t is t square mod n, mod 561. What is t square? The new value of t which we have found out is 263. So it is 263 square mod 561, and that will come around 166 mod 561. So we will go into the next step, that is k is equal to 2. So in this step, we consider that t is equal to t square mod 561. Now the new value of t is 166, so it will be 166 square mod 561, and that is coming around 67 mod 561. Now we have to go for the third step, because it will start from I value will be 1, so here it is 1, 2, and the last step will be k is equal to 3. So t will be equal to t square mod 561, and this t square is nothing but 67 square mod 561, and that is coming around plus 1 mod 561. So since you are getting that t is equal to plus 1, so it means this 561 is not a prime number, it is a composite number. So you can do for another number can be checked and tested, but if anyhow, if t is equal to t square in the last step, if we are getting that here it is minus 1, then in that case whatever number has been considered, that number will be a prime number. Let us check for another number. Suppose for 27 we want to check. So 27 means it is n, so n minus 1 will be 26. So 26 can be considered as 13 into 2 to the power 1, where m is equal to 13 and k is equal to 1. So, if m is equal to 13, so we have to go for the initialization process. We have to first calculate the value of t, and the value of t is nothing but a to the power m mod n. And what is the value of a? Here base is 2, so 2 to the power m is 13, mod n is 27. So 2 to the power 13 mod 27, it is coming around 11 mod 27. And since k is equal to 1, we will not go for the further, uh, because the algorithm says that I will be starting from 1 to k minus 1. Now k value is 1, so 1 to 0, it means it is not going to execute, and if it is not going to execute, the result which we are getting as a t is 11 mod 27, and we declare that this number is a composite number. So in this way, we are testing that the number is a prime number or not.